Hi, this is the 5th video in this tutorial series, and by now you know how to set up your federated learning pipeline completely. You know how to choose a dataset and partition it so every client gets its own data partition. You know how to design a Flower client and how to configure every method in the client so it can do things like local training using its own dataset or evaluating the global model using its own validation set. You know how to choose and configure a strategy, passing methods like onFitConfig for onFitConfig and for evaluation on the server. And in this video, what we're going to do is we're going to start a simulation. We will run the simulation first on CPU, and then I will show you how you can assign different type of resources to your clients so they can run on GPU. Towards the end of the video, I will show you also how you can carefully tune these settings so you can pack many clients on the GPU running so they all run concurrently. So our simulation is going to return us the history of the simulation of a federated learning experiment, and this history will contain metrics such as what was the validation accuracy of the global model after every run, and many other metrics that you can include in your experiment. So to start a simulation, we will do Flower simulation start simulation. And this accepts a number of arguments. One of the main arguments that we still haven't used from our main is the client function. So this client function is the one that the virtual client engine is going to call in order to spawn a client. Another important argument is to know how many clients there are in total. So you can do that with a variable called numClients that we know from the config file, and it's called numClients as well. Next, we need to config one of the high-level behaviors of our experiment, which is how many rounds of federated learning we want to do. And we do this by defining a server config. Because remember, the server is the entity that is going to loop over n rounds, and it's going to tell to the strategy, okay, we are doing fit. Prepare the fit, called configure fit. Is the configuration of the fit done? Okay, let's spawn the clients, and let's wait for all the updates to be received back in the server. Let's aggregate these different models into a single one, and then let's loop over another round. So this is going to be done on the server, and what we are going to be using is the default server, but even though it's a default, we still need to tell it how many rounds we need. We do this as follows. So Flower server, we want to specify the server config, and we need to set how many rounds. So we are going to set this from the config, which probably the name we were using is called num rounds, but let's be sure about it. I think I have this from here. All right, so it's num round. Let's make sure it is plural, which otherwise will be for sure a source of typos. And then the final argument we need to pass is what's the strategy we're going to be using. And this is it. This is everything we need to start a simulation. Well, these are the main elements to start a simulation. We can further configure it, and we'll see how to do that next. But first, let's run the code and see what happens. Oh, one small thing I want to mention is that I spotted a small bug in the fit method of our client. We return from the method by extracting the parameters of the locally trained model, and we do that by calling this getParameter method. But when we were writing this line earlier, we didn't pass anything here. And if you look closely, getParameters expects a configuration file. So if you don't pass anything, this will trigger an error. So make sure you have this set here. So now let's run the experiment just like this, and let's not do many rounds, so let's do just maybe 5 rounds. Let's do 5 rounds. and let's see how it goes. So first, as before, it's printing the config file in a convenient YAML format, and then this is telling us, okay, Flower simulation is a starting the virtual client engine initialized with resources, GPU resources, which are going to be highlighted here more clearly. 1 GPU, there are this many CPUs, and this is, well, the IP of the desktop computer I'm SSHing into. And we can see here that we are getting the log after every key stage of the simulation is completed. For example, we need to initialize the global model parameters, and we often do that by sampling one client at random. If this is not a behavior we want, what you need to do is to pass to the strategy when you create it what should be the initial state of the global model. This is something very useful, for example, if you want to start the experiment from a checkpoint of your global model, for instance. And then, before we start with the first round, we are evaluating what's the performance of the global model with a randomly initialized model. And as expected, this performance is pretty poor, and in this case it was close to 8%, which is close enough to random guess. We have 10 classes, so random guess will be 10%. And then we can see that we are starting the fit round number 1. We are sampling 10 clients out of 100, because that's what we set in our config, right? We said we have 100 clients. For fit, we're going to be sampling 10. We see that the fit round completes, and then it receives 10 results, meaning that all the clients did the job without crashing or anything, and 0 failures. What else is interesting here? At the end of the fit process, the evaluate method is being called. Remember this evaluate function that evaluates the global state of the model after aggregating. This is being printed here. You can see that after the first round that took this is the loss at that particular point, and then the accuracy is 27% already after just a single round. If we were computing many other metrics, that will go here, and it will be shown here for you. And this is the time it took to reach this point in seconds. Then once the fit method has been completed and we have evaluated the state of the global model, remember only if we are actually specifying a function here, then there is a eval round, which is going to sample randomly another set of clients. In this case, we are sampling 25 clients. 25 clients out of 100, because that's exactly what we said. And then the 25 clients are spawned in simulation, and they do federated evaluation, so running this method here. And then they return to the server, well, what was their loss in the local validation set and what was the accuracy. And this happens over and over for a number of rounds. So for example, here you can see at the end of the second round, accuracy was 45%. At the end of the third round, accuracy was almost 66%, and so on. And at the end of experiment, well, the history is printed for you, and you can see how the centralized metric, which was the accuracy we are obtaining here, went from 7% to 27, 45, 66, all the way up to almost 88. And we have access to all the other metrics as well. What was the centralized loss? The centralized loss comes from here. And interestingly, we have as well the validation, the federated losses, which are these ones here, which we see also going down, right? From 6.8 at the end of the first round down to 1.4. And you might say, okay, why I don't see the accuracies here, even though I'm passing them? Well, the reason for that is because there is yet another argument you can specify in your strategy, which sets how these metrics are aggregated. Because remember, here you could be sending anything. You could be sending the time it took to do the evaluation, or you could be sending how much, for instance, how much memory this particular client used. And depending on what you send, you might want to use different different rules to aggregate all these metrics or to discard them from aggregation entirely. So that's why by default, because we don't know what a user might use this for, nothing is being displayed. But you can specify it by setting a function here. Let's check it in the source code. It will be something like, it will be setting this parameter, evaluate metrics aggregation function, which if we look it, if we search for it, here you can see how it is being called. So at the end of the evaluation, there will be an aggregate evaluate being executed in the strategy, and here you receive the results and the failures. The results essentially contain everything returned here, where the main result is the loss, because that's the, not here, sorry. The main result is the loss, and this, because this is the fixed expected arguments, and then the second part are the metrics. And if you want to do something with the metrics, you need to define a function. So here you say, if this function is defined, you can define it from here. Let me extract all the metrics from my results, and let me evaluate that function. So that's something you would want to do if you want to make sense out of whatever you're sending back to the server. So we see that this worked fairly well. It didn't crash or anything, and we got to 87, almost 88% accuracy. That's a good result, but it's not a surprising result, right? Because in the end we have only 100 clients, and we are working with MNIST, and the partitions we are creating are identically distributed. So that makes the data heterogeneity problem super easy for this particular setup. But before we conclude this section, something else you might be interested in seeing is that, okay, now my experiment has finished. How can I save the history? Do I save it as a standard pickle? Is there a preferable place to save it? What's the recommended way of doing it? And now what we're going to be doing is, well, doing exactly that. If you have been running this code along while you were watching the tutorial, or maybe later, you might have noticed that there is a directory here that we didn't create, or we never specified it, which is called outputs. So this directory is created by Hydra, and inside outputs there is a subdirectory with the time. Well, there is a directory with the date, this is the current date I'm recording this tutorial, and then inside there is a time, yeah, right? Hours, minutes, and seconds. And each directory contains not only the log of the experiment, it also contains the particular config that was passed. For example, if you recall, the last command we ran was this one, Python num rounds 5, which we modify the default num rounds argument which by default is 10, and you can see that the config file in the experiment directory created automatically for me, it already reflects this change. So this is a pretty nice built-in feature in Hydra that you get for free if you use Hydra. So given this, one of the ideal places to save all your experiment results and checkpoints could perfectly be this directory, right? Because you already have the log, you already have the configs, so why not save the data? So one question here would be, okay, how do I get the path to that directory? So in order to do that, we're going to make use of one of the built-in features in Hydra, which give us the path. So for that, I usually do it as follows. So I import Hydra core, Hydra config, and from that I import Hydra config. And with this, what it allows me to do is to fetch what was that path that was created automatically the moment I run the experiment. So you can retrieve this, let's call it save path, as hydraconfig.get runtime output directory. There might be a different way to get access to this output directory path, but to me this is the one I've been using for a while. So if you know a different way, more convenient way, just let me know down in the comments, which will be very helpful for everyone. And let's say that we want to create our results and save them in a path to a file that we're going to call something like a results path, and it's going to be, say, save path, results pickle, and path is going to be a path from pathlib that we are going to import now. From pathlib import path. All right. So we're going to create a pickle, and in the pickles usually put, I don't know if it's a strict requirement, but at least I put everything inside a dictionary before saving anything. And something we might want to put in this dictionary is, for example, the history we just obtained from our experiment. Let's say that you want to save other things, like, I don't know, anything else. You would put it here. Else here, for example. So how do we save with a pickle? So probably you are already familiar with this, but I'm gonna show it just for everyone else to know. So this is the path to the file we want to create, the pickle file we want to create. We're gonna be writing it in write binary mode. We get in the handle, and then we're gonna do pickle. Yeah, pickle. We're gonna pass our dictionary, the handle, protocol is gonna be pickle highest. This protocol, we just need to import pickle. So just like that. So if we now run a very short experiment, for example, let's do 2 rounds, and then let's do also num-client fit equals 5, and num-client for evaluation, let's just do that. So if we reload this, we'll see that, oh, there is already one new directory created for this particular experiment, because this is the current time. And we are gonna let it run, and it should finish very soon. We'll see that a pickle called results.pickle should appear here. So if we refresh this, here it is. There is a results.pickle. Again, the config file reflects the fact that we changed it to just two rounds, and these many clients for fit and for validation. All right, something we discussed very early in the beginning is that with simulation you can very much adapt any federated learning workload to the resources that you have available. So if I have a laptop with just CPU, I want my clients to only use the CPU because there is nothing else. But if I take the same experiment and I run it on my desktop with 1 GPU, or on my server with maybe 8 GPUs, I want to still be able to not only make use of the exact pipeline I have defined, but make efficient use of the resources available. So how do we set the resources that our clients are going to use every time they are told to participate in a round? So we do that from the start simulation command. And the way we do this is by setting up a variable called client resources. And this client resources follows this client resources is a dictionary which needs to specify two items. One is called num CPUs, which sets how many CPUs should be allocated for a client that is doing work. Let's set it to 2. And the other one should be called num GPUs, which which is not how many GPUs we're assigning to a client, but instead it's the ratio of the amount of GPU memory, so VRAM, that a client should have access to. So for example, imagine I have, let's assume I have only one GPU. If I set this to 1.0, it means that when the virtual client engine is deciding to spawn 10 clients to participate in the round, they can all run, but only one at a time, because every client, I'm saying, that needs to have access to the entirety of the VRAM. If instead I set it to be, let's say, 0.25, well, with this I'm saying that my GPU should be able to run 4 clients concurrently. So as you can imagine, this is a very high level way of control the degree of parallelism of your simulation, because from a single scalar I can decide to either run 1 client concurrently or run, for example, 100 clients concurrently on my GPU. And this comes with a big, let's say, you can do a big change, but you have to be careful about this. So one of the most obvious things to consider here is, okay, how much GPU memory my clients need. In this case, for example, we know we are working on a very small model, small input images, fairly small batch size. So I think it's safe to assume that we are not going to use more than half of the VRAM of my GPU. And if you aren't sure how much VRAM your GPU has, well, you can do this in the terminal. If you have a CUDA capable GPU, you can type just NVIDIA SMI, and you will be seeing. So for me, here I have a GPU with 24 gigabytes. This is a 3090 Ti, which is pretty good, I think. It's not the best, but it's good enough for doing some development of federated learning workloads, and more than enough for this particular experiment. So I'm pretty certain that my clients are not going to use probably no more than 2 gigabytes. So we have plenty of room, but sometimes this might not be so obvious, right? So usually my advice is to start a simulation with a fairly conservative number here, and then let's see how it goes. So we are going to do exactly that. So I'm going to clean this, and I'm going to launch my simulation again. Let's set it again to 10 clients. And let's do a few more rounds, just so we can observe something happening on the GPU. All right, so let's run it. Oh, by the way, before we didn't set client resources. So by default, the client resources is 1 and 0. So by default, if you don't set them, your clients are assumed they are gonna use only 1 CPU core and 0 GPUs. So the previous examples we were running, none of them were using the GPU. So let me just do this command, which is gonna call NVIDIA SMI every half a second. And what we can see is that 3 things, right? We have the Python process here represents my global model. So because the evaluation of my global model, so this stage here, and because this is not under the control of the simulation per se speaking, under the control of virtual client engine, it doesn't care about these arguments. So that's what the Python process represents. And here we can see that there are 2 ray processes, which, if you remember, is the tool we use in the virtual client engine to spawn clients in the round in a resource-aware manner. And because we are telling the clients to use half the GPU at most, well, we are only capable of running 2 clients concurrently at most. And you can see that this is changing. What is saying here, it was running a function called launch and evaluate, which means we are launching evaluation clients, telling them to run the evaluate method, which is this one. And if you were looking carefully, you might have seen another function name called launch and fit, which what it does is to call clients and tell them to do fit. So, and we remember we only had 2 processes there with the array keyword because we told it to only use half a GPU. Let's run it again just for fewer rounds. Sorry about that. So we can make another observation. But yeah, for 4 rounds. So let me walk you through what's going to happen now. So the simulation is going to start, and the first thing we're going to do is we're evaluating the global model. So that's why this Python process exists, because it was evaluating the global model, which was so fast. And now we have 2 clients running, and this is a perfect opportunity to see what's the actual memory usage of my clients. So you can see it's less than 1.8 gigabytes. So that leaves me plenty of room to pack more clients concurrently. So what this is telling me is that, well, here I was very generous setting this 0.5, sorry. Maybe I can push it a bit more and use, let's say, 0.1. 0.1. Let's go 0.25, just to be safe at first. So if I do this will spawn 8 clients. This will spawn exactly the same clients per round as I'm defining all the time, in this case 10. But what it's going to allow me is, if the limitation is the GPU, what it's going to allow me to do is to run 8 clients concurrently in my GPU, so in parallel. Of course, assuming that I have 2 times 2 CPUs. So do I have 16 CPUs here? Well, I can tell you I have 24 CPUs, so I should be capable of running 8 clients concurrently. So let's see just that. All right, so, and of course this parameter, you can, here I'm setting it manually on the main, but you can define it from a config. So let's clean this and let's run the same workload again. Yeah, 4 rounds, 10 clients per round. So as you can see, the experiment, I haven't changed anything else in experiment. What I've only changed is how many resources my system should assign to the clients. And based on that, I will be able to schedule more clients concurrently. So you can see that I'm able of packing 8 clients in the same round, right? And they are all running concurrently. Idle means that the task representing this client has finished, and those resources can be taken by a different client. And you can see that I still have room to push a bit lower the NAM GPUs. I still have like roughly 8 gigabytes left. So yeah, and as you can see, this is running just fine, 8 clients concurrently. Yeah, now the experiment should be finishing, all the resources were freed, and that's it. So this is the main things to consider when you have reached the point of launching your simulation. So let's minimize this briefly. So launching your simulation requires you to pass this function that will spawn the clients. That's why we define it earlier like that. You need to tell it how many clients there are. You might want to set up how many rounds in total of federated learning we are supposed to do. You will be passing the strategy, because remember, the strategy is what basically orchestrates the whole federated learning process. And you might want to also customize the client resources that you want to assign to every client every time it is told to participate. Finally, the output of the start simulation is a history which contains all the metrics in your experiment. There are some metrics that are expected and therefore fixed in Flower. Like for example, if we go back to the client, metrics like the loss, right? The loss is always expected to be there. Or similarly in the evaluation method, where I'm gonna be evaluating the global model, it's also expected to return the loss. So because of that, those metrics will be aggregated correctly and incorporated into the history. If you have custom metrics, you might want to pass additional parameters to the strategy construction process to define how these extra custom metrics are aggregated. And if you do so, it will be reflected in the history. And then, very conveniently, Hydra creates a experiment directory for you based on the current time you are running the experiment. And this is the ideal place to go back and check, oh, what was the exact config I was running, and the ideal place to save your experiment results.